Hello, welcome to Math321. This is the University of Wollongong's numerical methods class in third year. I think it's actually called numerical analysis, but the class is a combination of both. Okay, so I'm going to start off by discussing this question. Is it possible for a computer to tell if a function is continuous? Okay, so in this particular case I mean a function from the real numbers to the real numbers, and of course the definition of continuity and I'm going to use this one. They're all, I mean, there's a lot of different ones and they're all equivalent in some sense, but I like this one because well, I guess I'm going to use it. So for all x in R and for all epsilon greater than 0, there exists a delta greater than 0, so that if y minus x is less than delta, then that implies that f of x minus f of y is less than epsilon. So in other words, if these two things are close, then this is close. One way to think about it is, here's our copy of R, and here's another copy of R, and our function f maps between them. Here's our point x, and we have some interval around it, x minus delta, x plus delta, and that interval gets mapped into the interval. Here's our f of x minus epsilon, f of x plus epsilon. So no matter how small this interval is, you can always pick an interval here so that f maps this interval into there. Okay, now, so in order to determine whether or not a function is continuous, we need to know whether or not all points in this interval get mapped over to here. So the computer has to do that calculation. For every single element in this interval, it has to work out, is that element in there? Now, checking if an element is in an interval is not too bad, less than or equal operators. But trying to do the calculation for every single point in this interval is impossible. It takes a finite minimum amount of time for the computer to do this calculation of f of some point for any point in there, and there's an infinite number of numbers in there, so that means an infinite amount of time that the computer would have to spend working out whether the function is continuous or not. And of course we can't allow a computer to run for an infinite period of time, so can't do it. Well, I can't do it using this approach. There are other techniques that might give you the information needed, but I can't do it doing this way. Finite amount of memory, and what I'm going to try and argue in a moment is that it can't actually represent it. The computer doesn't know all numbers in here. It's actually impossible, even if the computer could do an infinite number of calculations, because of the way our computers work. It's impossible for the computer to perform the calculation f of y for an arbitrary y in there. And even if we have y and we can represent y in the calculator, in the computer, it is, depending upon what the function f is, impossible to accurately calculate the value. So let me restate those three things. So impossible to calculate f of y for all y, because there are an infinite computer has finite memory, and therefore cannot represent all y's. So there are some numbers that the computer is physically limited to not knowing. Like, it's absolutely impossible for the computer to know what that number is. And depending upon the function, unable to accurately calculate f of y, even when y is known exactly. So these problems are basically the problems that underlie numerical methods in analysis. Computers have limitations, which mean that they're inaccurate, and we have to deal with those inaccuracies. And the calculations that they perform will introduce more accuracies. So we need to know what those accuracies are, and we need to know that the algorithms we use will work even with those inaccuracies. Okay, now there are, of course, if there are other ways to prove things, then it may very well be possible to prove that a function is continuous using some other technique on a computer. I mean, at least doing it directly like that is not good. So we think about the real numbers as a line. And one of the important properties of the real numbers is that for all x and y inside the real numbers, x less than y implies that there exists z in the real numbers, so that x is strictly less than z, which is strictly less than y. This is not true in a computer. The computer's real number line is discrete. So this is what I mean by computers cannot know all numbers exactly. There are some numbers that the computer is restricted to never knowing about. And this is there's a lot that can be said about numbers in computers, and I'm going to say a little bit about it. But there's a lot of this research was done a long time ago, so the books out there which contain this stuff are usually not too expensive. Go have a look up Dover. There's probably some in the library. I've put some names of books on the resources page, and there's lots of papers that you can find about this kind of thing, if you're interested in it. If you need some help looking for things, let me know, and I can point you away a little bit. Okay, so because the real number line is discrete, calculations performed on a computer don't necessarily behave the same way as calculations performed on a piece of paper on the real line, which means that you are more accurate than a computer. At least in theory, because you're going to take a lot longer to do the calculations, and it's much more easy for you and I to introduce errors and mistakes in the calculation. So, but we're not limited the same way computers are. So there's a huge amount of detail and statistics about errors and accuracies in computers, and in particular the distribution of errors and statistical analysis of errors and how they occur during calculations. So it's worth reading about it, and there, as I said, there are some links on Moodle if you're interested. In this class, what is important is that you know these problems, but not necessarily know all of the detail. You just need to be familiar with them and understand that there are issues that need to be addressed. Okay, so now let's talk about how computers represent numbers. Okay, so first, natural numbers. Natural numbers 1, 2, 3, 4. These are positive integers. Computers know these numbers and they know them exactly. If you do arithmetic with integers, you'll get exact answers, no errors. That's not really helpful when you're dealing with very complicated functions that don't necessarily only produce integers, and it's not particularly helpful when, for example, you want to talk about limits of things, because of course you're going to be taking a limit to a number, even an integer. You need to know about numbers very close. It's not helpful. But everything's exact, and there are tricks you can play. Famously, at the Apple, I'm not 100% famously, the Apple II used the result that n squared is equal to the sum from j equals 1 to j equals the integer. Yeah. So this is you can prove that. So this is the sum of all odd numbers less than n. So 1 is equal to 1. 4 is equal to 1 plus 3. What's the next one? 9. 1 plus 3 plus 5. Right, and so on. So this is used in integer arithmetic, so it's exact. And famously, the Apple II used this and an algorithm which I have a link posted to on the resources page to draw circles and ellipses, which I can't spell. Ellipsis. Anyway, you need to take square roots when you draw circles, and taking square roots when you only have integers available to you is not it's not easy. But there are some tricks that you can perform to get around it. Of course, this is a long time ago, and I'm not sure that any computer will do that anymore. The reason they did it on the Apple II is because they used a number system that meant that calculating square roots was going to take a long time. Okay, 2. Fixed point numbers. So I think this is the number system that the Apple II used. Fixed point numbers generally have a fixed number of digits. Let's say 6. So in this case, pi is equal to 3.14159, and we can write 0, 1, 2, 3, 4. So you get 5 decimal digits and always 1 in front. And if you have extra numbers in front, then you lose accuracy. So you can do calculations using this, and of course older computers used to. Nowadays, and certainly for any software that you're likely to use, they'll be using floating point numbers. So this behaves a bit like scientific notation, and all numbers are represented as a number times, in our case, because I'm using base 10 as my number system, 10 to the power of something. This bit here is called the mantissa, and this bit here is the exponent. And in your computer, both the mantissa and the exponent have fixed length. Right, just like here. Right, now this has some advantages because it means that accuracy can be controlled a bit better, and of course in a computer there are many more digits. Now for the calculations that I'm going to assume here, I'm going to assume that the mantissas have 3 digits after the decimal point, and the decimal point always has a 0 in front. And I'm also going to assume the exponent has one digit. And in a calculator, in a computer, that's not true. There's many more digits, which means everything's more accurate. But this will emphasize some of the properties that I want you to understand. Right, so back to it. Not for you, for me. It was a big break in there. Okay, so I'm restricting the number of digits because inside a computer, the computer restricts the number of digits these things have. But of course, I'm not using the computer's notation. I'm not using, computers represent everything in binary. I'm using decimal. That doesn't necessarily, that means that the numbers that cause problems might be different, but the existence of the problems is still there regardless of the number system. So yeah, don't need to worry about that. Okay, so with these limitations, pi ends up being 0.314 times 10 to the 1, 1 over square root 2, 0.707 times 10 to the 0. And something like pi over 1,000 is minus pi over 1,000 is minus 0.314 times 10 to the minus 2. That gives you an idea of what's going on. Okay, now, so here's the computer's number line. I've drawn it as a number, as a straight line, but there are of course gaps in it. So here's 0, and I'm always going to write 0 as 0.000 times 10 to the minus 9. And I've chosen here the smallest possible exponent. I mean, it's an arbitrary choice. The smallest exponent means that, if, for example, if a bit accidentally gets flipped, the change is smaller. I mean, this is 0, right? So it doesn't really matter what the exponent is, but if you want to make sure that there's some kind of numerical error that creeps in, that error is as small as possible, so that's why the exponent is smallest here. So what is the next biggest number? Positive. Well, I claim that it is. So why? Well, we're going to keep the exponent the same, of course, and this needs to be non-zero. So we could put a 1 here, or here, or here. We only have one digit for the exponent. If I put a 1 here, that's not valid notation, because I need to have a 1 here. The notation is that the first digit, I didn't really say this clearly, but anyway, the notation is that the first significant digit occurs directly after the decimal point, just like in scientific notation. So if you put a 1 here, the first significant digit does not occur. It occurs a few back. So, not a valid number. So the next highest number that is allowed in this particular notation is this one here. And there is a finite difference between them. And even if you do allow a 0 straight after the decimal point, you're still going to end up with a finite gap here. Of course, in the real number line, there are numbers in between. But in the computer's number line, there are not. What's the next biggest number? Next biggest number is, we already have one in the significant place, so now we can alter the last one. And again, we have a gap, smaller than the last time, smaller by 3 orders of magnitude, but smaller and finite gap. And so on and so forth. Okay, so this is an important point. For any fixed exponent, there are 900 possible numbers. Right? 0.1 all the way up to 0.999. And remember, that's because we're not allowed. That's because the first significant digit must occur directly after the decimal point. don't get hung up on this. Even if you're allowed the first significant digit to occur, at the end of the mantissa, you still have the same problem. There's a fixed number of possible numbers here, and even if you allow the first significant digit to occur before the decimal number, the decimal point, you still have the same issue. All of these are kind of what I would call implementation issues in the computer, a choice of the representation of numbers in the computer. Such choices have been pretty much standardized now, but previously they weren't. And on occasion, it was necessary to kind of know things like that because it made a difference. But nowadays, things are a little bit more abstracted, so it doesn't really matter too much. Okay, so this has an important implication. So the gap between, the gap between 0.1 times 10 to the 2 and 0.101 times 10 to the 2, the two closest, well, this is the next closest positive number to, what's that, 10, and that's 10.1, is larger than the gap between 0.1 times 10 and 0.101 times 10 to the 0. So let's have a look at this. This number here is 1, 2, this is 10, this is 10.1. So the gap there is the difference. Right. And now this is 0.1, and that's 0.101, and that difference is 0.001. So there's 2 orders of magnitude difference in the size between these things because there's 2 orders of magnitude difference in the exponent. So the point is that for a fixed exponent, there is a fixed distance between the numbers, which is it's 900 distribution. But when you allow the exponent to change, that fixed distance between the numbers differs, and that's what happens up here. This is the fixed difference between all numbers that have exponent -9, and this is a kind of special case, but illustrates the fact that there is a bigger difference there. Okay. Now here's another issue that crops up. So is is 0 the same as 0 with a minus sign? Okay. Well, some computers think so, and others don't. Again, an implementation issue that has important consequences. Okay. So I'm going to let epsilon squared be the number 1/2 times 10 to the -3. Now I'm using proper decimal notation. This is not the number in the computer, this is a specific number. So this is 0.5 times 10 to the -3, 1, 2, 3. So 0. 2, 1, 2, 3. Yeah, right. So a small number. So should there be an extra 0 there? 1, 2. Yeah. There you go. Okay, so not stored in a computer, but note that this number is too small to be stored. No. Sorry, I'm getting myself confused. This is a perfectly valid number to put into a computer. It's too small in comparison to another number that's going to come up in a moment. hold on a second, I have to think about this. I think I have been led astray. Okay, let's just ignore that. So consider this. One minus epsilon, 1 plus epsilon. Now algebraically, this is 1 minus epsilon squared, which is equal to epsilon squared. Now, let's suppose that epsilon is, as I mentioned, 0.5 times 10 to the minus 3. So 1 is equal to 0.1 times 10 to the minus 1. 10 to the 1. Equals what? 0.1 times 10 to the 1 minus 0.5 times 10 to the minus 3. Well, we can kind of skip slightly, right? So this is 1 minus 0.0005, which is equal to 0.9995. Now we have a mantissa which has only three digits in it, and this thing has a mantissa of 4, so we have to round it. Now, most rounding rules in a computer ensure that this would round up. So, in the computer's notation, this becomes what's the reason for this? Now, this is where we get back to it. So, in fact, you don't have to have specifically this, but this is because epsilon equal to 1/2 times 10 to the minus 3 is too small. It is smaller than the step size for numbers with exponent greater than or equal to 1. So this number can be represented in our computer. It's a computer's representation is which is fine. We can write that down. But the problem is when we add that to other numbers or subtract it from other numbers, we have an issue. So whereas the equation should be equal to epsilon squared, which is going to be equal to 0.5 times 10 to the minus 3 squared, 0.25 times 10 to the minus 6. Which can be represented on a computer. The actual calculation in the computer can't, because as intermediate steps 1 minus epsilon is represented in the computer as, and the same goes for this. So when you multiply these things together, you get, and hence 1 minus epsilon, 1 plus epsilon is equal to 1 minus 1. Which is a problem. Okay, well, apologies for the confusion there, but yes. Now, so this has the implication, you'll see this written somewhere, this is the implication that computers have two types of zeros. And this is only kind of a way of talking about it. Two types of zeros. There are proper zeros, and calculations that give zeros. But they're not really zero, they're just that the computer can't, isn't accurate enough to work it out. So this is an example of, there's a terminology for this, and this particular error, and it is called underflow. Okay, so underflow, definition. I hesitate to call it a definition because it's this terminology that's used. Underflow occurs when a calculation produces a number too small to be represented. That's not quite true. Occurs when a calculation produces, let's say, 0 when it shouldn't. And that's what happened in this particular case. 1 minus epsilon is in the computer equal to 1, and there's underflow. The difference between this number and 1 is too small for the computer to represent, and so it ends up being 1. Now there's overflow as well. So this occurs when numbers are too big to represent. So for example, 0.999 times 10 to the power of 9 plus 0.1 times 10 to the 1. What does that end up being? If you want to study this very carefully, and you want to look at bit notation, and you want to look at the representation of these in decimal, and you want to look at exactly how calculators do addition, then it is possible for this to be some number. Some computers will actually return whatever this is in the decimal notation, and the reason is because they just naively add the decimals together. They have an algorithm they follow, they naively follow it, even though they lose precision and they lose digits. That's called an overflow. Some programming languages and some computers will return errors if this happens, and some don't, so you have to watch out. Alright, and the last one I want to introduce is what I'm going to call an inexact calculation, where the calculation produces a number that cannot be exactly represented. And as I said, these aren't definitions, it's a mathematical definition. This is just language that people use to represent things where things are too small, things are too big, and where computers don't know about things. So we had pi previously. Another example would be 1/3. Again, I'm sticking with decimal notation here, but if you were in binary, other different numbers, and that probably this number as well, but other different numbers would not be exactly representable in the computer. Okay, so there's lots of errors. They occur, and you have underflows and overflows occurring, and there's gaps between numbers, and the size of the gaps changes based upon the size of the exponent. Okay, how to measure error? So because the size of the gap between numbers changes, it's often a very good idea to consider the relative error. So So this is where the true value of some calculation minus the calculated value divided by the true value, and so this is the error relative to the true value. So for example, pi minus 0.314 times 10 to the 1 divided by pi. This is roughly, and you might as well ask yourself the question, how did I calculate this? Well, I used a computer, which kind of begs the question, but anyway. So the relative error here is about 5 parts in 1,000. There's also absolute error, which is the true value minus the calculated value. So pi minus 0.314 times 10 to the 1 is roughly 0.001593, which says that the absolute error is roughly 1 part in 1,000. There's different circumstances in which you would want to use absolute error over relative error. Sometimes one will be more important than the other. I would generally recommend relative error because it's scale free. It doesn't matter how big the true value is, the relative error will allow you to compare relative error for calculations of different sized values, whereas absolute error does not. So if you do a calculation with a very big number, you're likely to get a very big error. If you do a calculation with a very small number, you're likely to get a very small error. And the reason for that is because the distance between points on the computer's number line are big for big numbers and small for small numbers. And if you want a measure of error which ignores those differences, you need to use the relative error. But when the true value is very small, this causes problems itself, because of course you have to calculate the relative error on some machine, and a very small true value distorts. It also can introduce errors that you don't want to be involved with. For example, sine pi minus sine 0.314 times 10 to the 1 divided by sine pi is not something that makes a great deal of sense. So some people have advocated using the max of whatever the value is that you're calculating, in this case pi, and the value of the function. So this would be replaced by pi in circumstances like this. So they're suggesting use this instead of the true value of the function. Still problems because both x and the value of the function could be small, but it's a small step, small thing to add into a computer that might help in many cases if you ever need to actually code something like that up. Right, so all of this begs questions. Evaluation of functions. So you've seen that the number line, the computer's number line, is discrete. You've seen that there are gaps. You've seen an example of underflow. Overflow is pretty obvious, and you've seen that there are numbers that are inexact that can't be represented exactly, and you've seen some measures of error. All of this kind of begs the question of how do you evaluate functions, because if you have these problems with the number line, surely evaluation of functions on a computer is problematic, and it is. There's again, just as there is a great deal of literature on the representation of numbers in a computer, there is a great deal of literature on the evaluation of functions, particularly special functions. By which I mean things like exponents, trig functions, and more special things that you might see like Bessel functions, gamma, etc., etc., etc. Right. So there's a lot of these things, and there's whole algorithms devoted to the evaluation of these things. When I did my PhD, this is back 2004, right, 2006. Yeah, something like that. There's a fellow I worked with who came up with an algorithm for evaluating a certain function that occurred a great deal in optics. This is highly oscillatory, and that makes calculating its integral very difficult, and he invented an algorithm specifically for this particular function, and that resulted in him getting a job from working in their numerical team. So there are still open problems here. Anyway, there's some general rules. And one of them is re-expressing. So picking expressions for things that are better, that are good for computers. Okay, so consider the quadratic equation. Ax squared plus bx plus c equals 0. Solutions to this we write using the quadratic formula. Minus b plus or minus the square root of b squared minus 4ac divided by 2a. Now, when 4ac is very small, this is roughly b squared, and one of these terms is going to be something minus something, basically the same size, and as we've seen before, that causes problems because you can have underflow occur in these circumstances. So when b squared minus 4ac is very approximately b squared, underflow can occur. So that causes a problem, and you want to avoid it. Now, importantly, only one of these expressions will have underflow. So the square root of b squared is going to be, so we're always going to choose the positive root. We have plus or minus there. So when b is positive, underflow may, not always, but may occur for the plus root. For the minus root. No. Yeah, the plus root. We have minus b plus something which is very close to b. And when b is less than 0, underflow may occur for the minus root. Because then we have minus b, which is positive, minus something that is close to b, and that's say the absolute value, right? So that's positive, and that's negative, so it could be close to 0, and that's positive, minus something that's positive. So yeah. So you can avoid this. So if we assume the other root, of course, will be fine. So no problems here. So we'll assume that b is greater than 0 just to avoid this. So we want to avoid calculating the minus b plus b root to avoid underflow. We can calculate one root as x equals minus b minus square root b squared minus 4ac over 2a. So we avoid underflow, and we get something that is, reasonably accurate. Or at least we avoid an obvious problem, right? So how do we get the next root? Well, consider this equation: ax minus x1, x minus x2. So we have the two roots in here. If we expand this out, we get ax squared minus a times x1 plus x2 plus ax1 x2. And this implies, because this is equal to ax squared plus bx plus c, that we have ax1 x2 equals c, or that the product of the two roots, right? We can rearrange this. So if we assume that we can calculate x1, then this implies that x2 is going to be equal to c divided by ax1, and we have avoided possible underflow. no guarantee that the underflow would have occurred, but we've employed a possible underflow. The point is, sometimes computers need things to be expressed in a way which makes better sense to them than it does to us. Because it doesn't make any difference to us. We can do our calculations exactly. A computer cannot. Here's another example. Square root x plus 1 minus square root x. So for very large numbers, these two things are the same, and we're likely to get underflow again. This is equal to the square root of x plus 1 minus the square root of x times 1, square root x plus 1 plus the square root of x, over square root x plus 1 plus the square root of x, and this is equal to 1 over x plus 1 plus the square root of x. When x is very large, this is a much more reasonable thing to calculate. Of course, then you're dividing a small number by a large number, and there are other problems incorporated in there, but you get the idea. As an example, series expansion. And this is something that's used very often. In fact, you'll find some expansions hard-coded into certain code. So let's say you want to calculate sine x over x when x is very small. Well, this is x minus x cubed over 6 plus x5 over 120 minus, etc., divided by x. And this is 1 minus x squared over 6 plus x4 over 120 minus so on. And now you can see that you can do the calculation. You're not dividing by something very close to 0 anymore. You're plugging 0 and you're plugging something in close to 0, and these things will get 0, and the answer is probably going to be close to 1, rather than what would likely happen is that you end up the computer error is involved gets blown up out of proportion, and the number might end up being very large. Mean value theorem. These are all just tricks. The point is to try and re-express the whatever you're calculating in a way that the computer finds easier to understand. So the mean value theorem, if f is a function from the real line into the real line, is continuous and differentiable, then for all a and b in the real line, a less than b, there exists some number which I'm going to call theta between a and b, so that f minus b, f of b minus f of a is b minus a times the derivative of the function at theta. Okay. So the point is that if you take an estimate of what theta might be, you can end up with something that could be, possibly, very accurate. Now you need to do some analysis to determine if that's the case. Here's an example. Log of b minus log of a. Right, so here f of x is equal to ln of x, and the derivative of f of x is equal to 1 over x, which implies that, there exists some theta, so that ln of b minus ln of a is equal to b minus a over theta. What to pick for theta? Well, one guess for it would be to use the midpoint, in which case theta is equal to b plus a over 2, right? We have the real line, there's my a, there's my b, and there's my theta in between. So this gives an approximation. ln of b, the log of b minus the log of a, is approximately equal to b minus a over b plus a 1/2. That turns out to be very accurate for certain ranges between a and b, and you can do some analysis on that to work out exactly when that would be more accurate than calculating the logs directly or using a series expansion or whatever. And that's what this class is about. When is an approximation like that a very good thing? We're not actually looking at function evaluation, but I want to introduce it to you. Now, I showed you the clever trick with the apple II. So sometimes coming up with a different algorithm, again, a new way to re-express things, can work quite well. And lots of effort has been put into studying particularly polynomials. And the principal reason for that is because special functions are usually represented in code or in scientific libraries as polynomials. So you want a good way to be able to evaluate the polynomial exactly. And just as a general rule of thumb, and just to make sure that you have seen this, because if it comes up, you would be expected to know it by some people, is don't calculate polynomials like this. For big numbers, you get overflow, and for small numbers, you get underflow. Not sensible. It is better this reduces the chances. Or maybe I should say that reduces the range of numbers in which underflow and overflow occur. And you can also show that it has slightly better numerical properties, meaning that the errors that you get are slightly reduced. So, that is a very, very brief introduction to numbers in a computer and evaluation of functions. Now, what I've represented to you is really just kind of shown you a bunch of different facts about this, and I haven't really synthesized all of that for you in some nice kind of coherent framework. Such frameworks are out there, and you can go read about it, but we're not so interested in it for this course, and there are links and some information about it that I've provided in the Moodle site for you to have a look at. And I suggest if you're interested that you go read about it. A lot of people have studied this kind of stuff, and there's a lot of information about it, because having good understandings of error in calculations is really, really important. And I will talk about that in the next video.